Okay, we're going to look at basic set concepts here. This comes from section 2.1 in our textbook. So a set is just a collection of objects. So oftentimes we'll use a capital letter to denote a set. So set A, let's say in this case, is equal to the letters A, B, C, 1, 2, and 3. Okay, so this is a set. It's just a collection of objects. There's 3 letters, 3 numbers, and you can have other things. I could have a set of students or a set of cities in Iowa or whatever. Okay. So this has 6 objects or 6 elements. So I could write the number of elements in set A is equal to 6. So this symbol represents the number of elements in whatever set you have inside the parentheses. Other notation here, I could say something like B is an element of set A. So this symbol, it looks like an E here. This means is an element of. So I'm saying that B is one of the elements in set A. B is an element of set A. I could also say something like 17 is not an element of set A. And what I would do is I would cross out the E symbol. And this is a way of saying 17 is not an element of set A. Okay. Now, I could, if I wanted to say, let's say A and 1 are elements of set A, I could say A, comma, 1 are elements of set A. These 2 elements are elements of set A. So you could do it with multiple elements. But one thing is you want to make sure that you don't put this in brackets like this. Okay, this would not be an element of set A. This would actually be a subset of set A, and we're going to talk about that in the next section. So the elements are just A and 1, but you wouldn't put brackets around it. If you put brackets around it, then it would not be an element of set A. Now, when you make a set like this, what we do, one of the ways we can refer to the set is by actually listing out all the elements and putting it in these brackets here. And they take a little bit of practice, but once you get the hang of it, they're not too bad. Now when you list them out, the order of the elements doesn't matter. They can be listed out in any order. This is a natural ordering, and so it kind of makes sense to list them like that. But however they're listed, it would be the same set. So sometimes they might use a circle to represent set A, and it includes the letters A, B, C, 1, 2, and 3. And so this kind of emphasizes that it doesn't matter what order you list them out in. Set A is referring to the collection of these 6 objects. Okay. Now there's 3 ways to denote a set. The book gives you 3 ways. Okay, the first way is roster form, and this is the form that I've been using, where you just list them out in brackets, like A, B, C, 1, 2, 3. Okay, that's roster form. Now I could use it even, let's say, I'm going to call this bold N. Okay, that line there means this is like a bold N. And this refers to the elements 1, 2, 3, 4, and ... means and so on, keep going. Now this would be an infinite set. This here means you just keep listing the next number, and you just go on and on and on. And you get actually the set of natural numbers. So this bold N is reserved for the set of natural numbers. So you could do other sets, other infinite sets like this. What do you suppose this set would be? 2, 4, 6, 8, dot, dot, dot. What do you think that set is? So if you said the set of even natural numbers, you'd be right. And so the idea is if the pattern is easy enough for people to see, you would start the pattern out and then dot, dot, dot. And then that would refer to an infinite set. This is a set of even numbers. Another thing you could do, I could let set H be the set 1, 2, 3, dot, 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 and then stop at 100. Okay, so now this would be the set of numbers 1 to 100. And it's not an infinite set anymore because I kind of put a cap on the end there. And so you go 1, 2, 3, and so on until you get to 100. Okay, so this is known as roster form. Now, a second way you can describe a set is using a description. So I might use description. If I'm interested in like the set of all Hawkeye students, I could let the set H equal the set of all Hawkeye students. Move that over a little bit. Enrolled in spring of 2019. That's actually the spring here. But this would be a way of listing or of describing the set of all Hawkeye students. Notice this is probably a much better way because if you were to do it in roster form, you would actually have to list out every single name, and there's over 2,000-3,000 Hawkeye students, and so you would have a list that went on, and even after listing out all the names, you wouldn't even know what that set was. You wouldn't know that it was a set of Hawkeye students, which is probably what is of interest in this case. So it makes sense that you would actually describe the set in this way. That's what makes sense. So you have to be careful, though. Let's say I did this. I described a set. I'm interested in the tall Hawkeye students. So the set of, we'll say, tall Hawkeye students. The set of tall Hawkeye students, we'll say, enrolled in spring of 2019. Well, the problem with this is how do you know if a student is in the set or not? What we would say is that this set is not well defined. So when you describe a set, the description has to be well defined in that it has to give an objective criteria for deciding whether or not someone's in the set or an object is in the set. So a possibility for this one, if we wanted it to be well defined, might be something like this. The set of tall Hawkeye students, well, we could say maybe the set of Hawkeye students that are 6 feet or taller. So we have to give some criteria that would kind of separate the tall students from the ones that are not tall. It might not be perfect, but that's what you need in order to use a description to describe a set. You have to make sure that it is well defined. Okay? The final way of describing a set, of kind of denoting a set, would be something called set builder notation. Okay. Now the way that your book uses this is kind of redundant. You might wonder why they would even have this. Let me give you an example. Let's say I want set S here to be maybe the set of states in the United States. So I could say the set S is equal to all X such that X is a state in the U.S., United States. So this is all elements X. The line there is read such that X has this property. Okay? Now this is kind of redundant because you might say, why not just describe it? Let S equal the set of all the states in the United States. Then it would be well defined and that would work. And you're absolutely right. That would be a fine way of denoting the set, okay? So when the book uses it, it looks kind of redundant, but this is actually important when you do math, especially as you go on and you try to do some of the more abstract proofs. This is used a lot. So let me just give you one example. You don't have to worry about this, and in fact, we're not going to use set builder notation very much. You probably won't see it on the test. So the reason I'm showing it is because you will see it as you read the textbook. Okay, so this isn't necessarily the way that it would be used in further math classes. So let me give you an example. Let's consider the set of all proper fractions between 0 and 1. Okay, now notice this, it would be very difficult to list this out. In fact, impossible, because what would the first proper fraction be right after 0? Would it be like 1/10, or maybe 100th, or 1,000th, 1,000,000th, 1,000,000,000th? As you can see, that just would go on and on. So there is no first fraction right next to 0 to start with. And you can just see then that listing these out in roster form is not going to work. So the best way to denote this set would be, and we'll use F here for like proper fraction. The way that they would do this using set builder notation is you would say all elements P over Q such that P and Q are elements of the natural numbers and P is less than Q. Okay, so that's how they would do it, and that's probably the best way you could denote that particular set. This says they're all fractions, where these are natural numbers, and the top is smaller than the bottom. That would make them fractions between 0 and 1. And this would actually give you all the fractions between 0 and 1. So I'll let you just think about that. You don't have to worry too much about it, but that's a pretty good example of how set builder notation is used in the real world. They probably would never use it like this. They would just use a description. Okay? So a few other concepts in this first section here. Two sets are said to be equal if they have the same elements. Okay, let me give you an example here. Let's say set A is A, B, C. And then let's say set C is B, A, C. Something like that. Set A and set C. Oh, I was going to say C, A, B. And it would, so that's why I said set C. That's okay. So set ABC, set BAC. Notice these two sets have the exact same elements, so they're really the same set. A is equal to C. Okay, so remember the order doesn't matter. It doesn't matter how you list them. They're the same sets. Okay. Now the other term here is equivalent. We say two sets are equivalent if they have the same number of elements. Okay, not necessarily the same elements, but they have the same number of elements. Okay, so let's say set A was A, B, C. And then we can say set B, let's say, is 1, 2, 3. Those are our two sets. Well, A is not equal to B. They don't have the same elements. But they do have something in common. Both of those sets have 3 elements. And so what I could say is that the number of elements in set A is equal to the number of elements in set B. They're both equal to 3. And so we could say that the two sets are equivalent. And in fact, we would say that to determine whether two sets are the same size, you would actually see if they're equivalent. All sets that are equivalent to these two have 3 elements, and we would say that the cardinality of the set is 3. So cardinality is kind of the mathematical term used to describe the size of a set. And any set with 3 elements would have a cardinality of 3, and they would be equivalent to these two. The reason for talking about it like that, instead of just saying the size of the set, is that when you start dealing with infinite sets, you actually show sets are equivalent, and they have cardinalities, but now the cardinalities are not numbers. If the cardinality is a number, it's a finite set that has that many elements. But infinite sets are they have a cardinality, they have a size, and two infinite sets, which could seem very different, can have the same cardinality. And I'm not going to show this, but for example, the set of natural numbers and the set of even natural numbers, it can be shown that they have the same cardinality. So they would say that they're the same size or the same type of infinity, but you wouldn't assign a number. And it's pretty counterintuitive, because it seems as if there's more natural numbers than there are even natural numbers, but they have the same cardinality. Okay, so the final concept that we're going to talk about is the empty set. The empty set is actually the set that has a cardinality of 0. Okay, so it is the set that does not contain any numbers. Okay, there's 2 ways to denote the empty set. You can put empty brackets like this, so that when you look at it, it's actually empty. It's like you're looking inside and you don't see anything. I like this because it kind of gets across the fact that the set is empty and the cardinality is 0. Another way to denote it, and this is kind of the way throughout math history, it was always denoted with a circle and a line through it, and they would call it the null set, and that's okay too. Okay, you could denote it this way or that way, and they both mean the empty set, and they both have a cardinality of 0. Okay, now you want to be careful. Don't use both symbols at the same time. And what I mean by that is, don't do this. Don't put the null set inside the brackets, because now you actually don't have the empty set anymore. You have the set that contains the empty set. There's actually one object in this set, and the object just happens to be the empty set. And that has a cardinality of 1. Okay? So the cardinality of this would equal 1. There's one element in there. Okay? But the cardinality of both of those is equal to 0. So you don't want to put the brackets around the empty set. Choose one or the other, and I would just stick with it. And I like this one. I think that gets across the idea of the empty set much better. Okay, so that concludes the basic concepts of sets.